Hello class. Now in this lecture we will see the first law of thermodynamics for controlled mass system. But this law is for the any general process. In the previous lecture we have seen a first law of thermodynamics for a cyclic process. But no, there is no chance all the process will be a cyclic. There may be a single process also there. For example, I have shown here PV plot. So there is a states that is 1 and 2 which representing initial and final state. So in between initial and final state there are path I have drawn over here. So this forward path is there and some reverse backward path is there. Okay, so whatever the law or derivation we have derived in the previous lecture will be applicable for cycle. For example, system transform from 1 to 2 and it will come back 2 to 1 via any of this returning path B or C. So it to form a cycle. So for that process it will applicable. But if system travel or transform from 1 to 2 but it won't come back, then it will be a process or system or travel from 2 to 1 and it won't again go 1 to 2, or I meant to say only for single path if there or single transportation is there, no not system going to again back to their previous case. So it is single path, single process there. So for that purpose that law will not be applicable, or for that derivation is will not be applicable. So here we supposed to derive a first law of the expression for first law of thermodynamics for any general process. Okay, so it may be a for forward process or backward process. Okay, so any process we can supposed to apply that. Okay, so just consider the derivation we have derived or the expression we have derived from the previous lecture for cyclic process, control mass cyclic process. So this is a expression that is cyclic integral of del q is equal to cyclic integral of del w. So here we are supposed to apply this expression for cyclic process A to B, means our system transforming 1 to 2 via path A and it come back to 2 to 1 via path B. So process 1 to B. So it is a cycle. So we are applying this process to cycle 1 A 2 B 1. Okay. So now here we are supposed to take care of all heat interaction equal to all work interaction during this cycle. So during process 1 to 2 via path A, all the heat interaction, that is integral of 1A to 2A of del Q. Okay, so here del Q along the path A between state 1 to 2. So all the heat interaction means all the heat addition or rejection during this process 1 to 2 via path A plus integral of 2b to 1b of del q, means all the heat energy added to the system or rejected by system to surrounding while performing process 2 to 1 via path P equal to integral of 1a to 2a of del w, means all the work interaction by system to surrounding or surrounding to system during the process 1 to 2 via path A plus 2b to 1b integral 2b to 1b of del w. Okay, all the work interaction during process 2 to 1 via path B. Okay, so it means all the work done by system to surrounding or surrounding to system, that we have to take care by this term. Okay, so mean to say all the heat interaction during process 1 to 2 2 to 1 equal to all the work interaction during process 1 to 2 2 to 1 in the entire cycle is equal. So summation of all heat interaction equal to summation of all work interaction during process A to B or during cycle A to B. Similarly, we are supposed to apply this expression for the process A to C, that is now we are considering cycle 1A to C1, this cycle. Okay, so same way we are considering all the heat interaction during the process 1 to 2 via path A plus all the heat interaction during returning process 2 to 1 via path C equal to all the work interaction during path 1 during process 1 to 2 via path A, and plus all the work interaction during process 2 to 1 via path C. Okay, so now we have got a two expression, this equation 1 and equation 2. Now subtract equation 2 from equation 1. So here we are supposed to subtract equation 2 from equation 1. So here some terms are look like commons. So here 1a 2a integral of 1a 2a of del q. Here also 1a integral 1a 2a of del q will supposed to cancel here. After that, opposite side of equality, that is 1a 2a of integral del w, 1a 2a integral of del w will be common. They also uh, cut cancel by each other. After that, at the end we will see it will be integral of 2b 1b of del q minus integral 2c to 1c of del q equal to integral 2b to 1b del w minus integral 2c to 1c of del w. All common term get cancelled and we will get at the end this expression. Okay, so now we are rearranging those this term. Shift this to integral 2c to 1c of del q this side, and this term to integral 2b to 1b del w this side. Okay, you will get this expression. Now take that integral 2b to 1b, integral 2b to 1b common, so you will get it integral 2b to 1b del q minus del w. Similarly here also take common integral 2c to 1c common, so 2c integral 2c to 1c under the bracket del q minus del w. This will be the expression finally you have got after this subtraction. Okay, and rearranging the term. So now if you have a look of this term, you supposed to notice that here we are subtracting all the heat interaction minus work interaction during the process 2 to 1 via path B, during the process 2 to 1 via path B, equal to all the heat interaction minus work interaction during the process 2 to 1 via path C, 2 to 1 via path C. So as we have seen in the previous lecture, heat and work are path function, means heat exchange along this path and heat exchange along this path will not be same. Even work is also path function, so work done along this path and work done along this path will not be same. Then how their difference, means how the difference of two path function will be same, belongs to two individual path, belong to two different path. Okay, but it is there, and it says that a difference of two path function is a point function because those paths are drawn in between two common state or two common path, that are two common point, sorry, draw in between two common point or two common initial and final state. Okay, so any path drawn in between these two common state 1 and 2, okay, whatever the heat energy interaction minus work energy interaction belongs to n number of path drawn in between these two states will be same. What I say, all the subtraction of heat interaction and work interaction take place during the any path drawn in between those those common states 1 and 2 will be same, even though path will be different. Then also subtraction of two path function will be same. Okay, so that term we have to indicate, that term we have need to indicate by another term like total energy. So we are here supposed to indicating or expressing that by a dE, their subtraction we are expressing as a dE. So integral of 2b to 1b of del q minus del w is equal to integral of 2c to 1c of del q minus del w equal to dE. So it is nothing but the subtraction of heat energy, all heat energy interaction minus all work energy interaction along the any path drawn in between two common states will be dE, and it is same. It don't depend on path. So here TE is a point function, and it is only valid for common states, whatever the process drawn or whatever the process take place in between two common state, initial and final state. If for example, if another 2 3 is present, and if I draw along the 1 and 3, then it won't matches. I said it is a drawn or process done during a two common state. So here we will have a DE is equal to change in kinetic energy plus change in potential energy plus change in internal energy. And D, that term we have familiar already. This is nothing but a total energy. We have seen already in our previous lecture. So total energy is nothing but the change in kinetic energy plus change in potential energy plus change in internal energy. So here we will have another expression, del Q minus del W is equal to dE. So this expression will be applicable to any process 1 to 2 or 2 to 1. If n number of path also there, for that individual path also it is applicable. So del Q minus del W is equal to dE. Now if we talk about the control system or control mass system, then inside the total energy, the change in kinetic energy, change in potential energy and internal energy is present. So in case of the control mass system, during the transformation, a change in kinetic energy and change in potential energy is negligible. Okay, all the heat energy, if absorbed by that system, are supposed to store as an internal energy. Okay, and whatever the energy, kinetic energy and potential energy of system have during the transformation will be negligible. Okay, so for that purpose, control mass system, we can remodify that this expression, that is del Q minus del W is equal to du. Okay, so need to be notice here that total energy will not be I mean to say a change in kinetic energy, change in potential energy will not be zero always. If it is mentioned, it have some considerable amount of change in kinetic energy, then or changes some considerable amount of change in potential, then we have to consider. But in case of the control mass system, there is a habit or there is an assumption, if not mentioned in the problem statement, then consider change in kinetic and change in potential is zero, and only we are considering internal energy for the control mass system. But in case of the control volume system, all those three we have to consider. Okay, that we will see in the steady flow energy equation. There is another version of first law of thermodynamics for control volume system. So till here we have completed the first law of thermodynamics for control mass system. So another again we have to summarize this lecture. The first law of thermodynamics, as per the first law of thermodynamics, we can see a change all the heat interaction during the process minus all the work interaction during the process equal to du. Or in simple way, if I put that del W in this side, okay, it will become del Q is equal to du plus dW. Sorry, it will become del Q is equal to du plus del W. Okay, so what it means? It means it means if Q amount of heat energy is supplied to the system, okay, then out of that Q heat energy, W amount of work done by system and du amount of heat energy stored in the system. I have to I supposed to write that expression, okay, for simplicity. So here Q is equal to U plus W. So here I have not written del Q and del W or du. I have directly you're using Q, U and W. So if I shifting this del W this side, then it will become like this. Q is equal to U plus W. Just consider it is del Q, del W and du. So what it means, if Q amount of heat energy is supplied to the system, then out of that Q amount of heat energy, W amount of work done is there, and U amount of energy stored into the system as the internal energy. It is as that simple. And during a two common states 1 to 2, if any process during along the any process, if transformation is take place of system, then it will be a same. Q is equal to U del Q minus del W is equal to du. and all the heat interaction during all the heat interaction minus all the work interaction equal to du, and that will be same along any process drawn in between a two common state, initial and final. Okay, so this is your first law of thermodynamics general equation, which is applicable to any process. I hope you have understand this thing. It is very important because on that basis only we supposed to derive a steady flow energy equation. Okay, and you have to first of all make sure that you have understood this first law of thermodynamics for any general process. Okay, if you feel any difficulty, please do comment in comment section. Thank you.